네, 먼저 제 소개부터 하겠습니다. 저는 이환용이고요. 아주대학교 산하협력 중점 교수입니다. 저는 2004년부터 크로노스 그룹에서 활동해 왔고, 크로노스 그룹과 ISO IC JTC1, SC24, 워크그룹 12, 그다음에 ISO TC17에서 크로노스 그룹과의 리에이종으로 활동하고 있습니다. 그리고 크로노스 그룹에서는 현재 오픈VG 스펙 에디터를 맡고 있고 한국 담당을 맡고 있습니다. 네, 오늘의 연사들을 소개해 드리겠습니다. 제일 먼저 TTA의 구경철 표준화본부 본부장께서 인사 말씀을 해주시겠습니다. 네, 구경철 박사님은 TTA의 표준화본부의 본부장님을 맡고 계십니다. 오늘 이 행사는 TTA와 공동 주최를 하고 TTA에서 번역에 대한 비용을 지원해 주셨습니다. 다시 한번 감사드립니다.
안녕하십니까. TTA 표준화본부장 구경철입니다. 만나 뵙게 되어 반갑습니다. 먼저 오늘 크로노스 그룹과 TTA가 크로노스 가상 오픈하우스 국제 행사를 공동으로 개최하게 된 것을 매우 기쁘게 생각합니다. 특히 크로노스 그룹 닐 트레벳 회장님, 슈리닉 세들기 회장님, 그리고 브렌트 이스코 회장님, 바쁜 일정에도 불구하고 본 행사에 참가해 주신 많은 여러분들께 깊은 감사를 드립니다. TTA는 ICT 표준화 및 시험 인증 전문기관으로 지난 30여 년 동안 글로벌 표준화 활동을 기반으로 국내 ICT 산업 발전을 위해 끊임없이 노력해 왔습니다. 이 일환으로 TTA는 매년 약 300여 명의 ICT 국제 표준화 전문가를 선정하여 ITU, ISO, ICJTC1 및 크로노스 그룹 등 공식 사실 표준화 활동을 지속적으로 지원하고 있습니다. 아무쪼록 코비드-19로 인한 뉴노멀 시대에 맞춰 온라인으로 진행되는 오늘 행사를 통해 크로노스 그룹에서 진행 중인 표준들에 대한 최신 정보와 표준화 노하우에 대해 많이 얻어가실 수 있는 계기가 되기를 바랍니다. 마지막으로 본 행사에 공동 주최를 할 수 있도록 진행해 주신 국제 표준화 전문가 이환용 교수님께 다시 한번 감사드립니다. 여러분의 가정의 평안과 행복이 가득하시기를 바랍니다. 감사합니다.
네, 첫 번째 발표는 닐 트레빗 크로노스 그룹 회장님이 크로노스 그룹에 대한 개요를 설명드리고 오픈CL 그리고 Gltf에 관련된 표준화 동향을 설명해 드리도록 하겠습니다. 닐 회장님은 엔비디아의 개발자 에코시스템 담당 부사장님이시고요. 그 다음에 크로노스 그룹의 회장 그리고 동시에 오픈CL 그룹하고 오픈VG 그룹 등의 워킹 그룹 의장도 함께 맡고 있습니다. 그래서 오늘 이 시간에는 오픈CL 병렬 처리 헤테로지니어스 플랫폼인 오픈CL에 대해서 설명을 해주시고요. GLTF 3D 어셋 표준에 대해서 설명을 해주실 예정입니다.
Hi everyone, I am Neil Trevitt. I work on developer ecosystems at NVIDIA and I am president of the Khronos Group. And I'm going to give you a quick introduction to Khronos, including our goals as a standards organization, a summary of our most active open standards, how we are organized, and hopefully convince you to get involved if you are not already a member. Let's start with our basic standardization question. Just what is an open standard? An interoperability standard enables precise communication, such as between a client device communicating to a server or an API that enables a software application to drive a hardware device. The tech industry uses thousands of standards. They are essential to removing industry friction and to grow market opportunities for everyone. The need for interoperability between hardware and software is growing as hardware technology continues to diversify and software seeks to become portable across multiple platforms and generations of silicon. The definition of a truly open standard is that is not controlled by any single company. And that means we need industry cooperation between multiple companies to create and evolve them. The industry uses standard developing organizations, or SDOs, to enable multiple companies to work together to form a consensus on open standards that move the industry forward. They work under well-defined multi-company governance and IP frameworks, and each SDO has their own area of expertise. Khronos is one of these industry standard developing organizations, an open standards consortium. We provide a safe place for the industry to cooperate and create interoperability standards that enable applications to access the power of 3D graphics, virtual and augmented reality, and parallel computation. We are a non-profit organization, and all the standards we create are open and royalty-free for the industry to use. We have been creating standards for 20 years and have almost 160 members that include everyone from the largest companies down to small startups. Any company who wishes to join Khronos is warmly welcomed to participate, to have a voice and a vote in how Khronos standards evolve. Here are the standards currently being most actively developed by Khronos. There are 4 main groups: 3D acceleration APIs, including Vulcan, OpenCL, and the new Inari API for analytic rendering. Initiatives around 3D asset formats, including Gltf and 3D commerce. The Openxr API standard for portable, augmented, and virtual reality. And on the right, a family of APIs and languages for parallel computation, vision acceleration, and inferencing, including OpenCL, SYCL, Sphere, and OpenVX. In addition, with the increasing use of open API standards in safety-critical markets, such as autonomous driving and robotics, Khronos has developed safety-critical variants of its OpenGL and Vulcan 3D APIs, designed to reduce the safety certification costs of systems that use them. Together with a safety-critical advisory forum, which is free and open for anyone in the industry to join to help create guidelines on how best to design APIs targeting safety-critical markets. Khronos standards are often used one at a time, but synergies often arise when they are used together in specific market segments. Khronos identifies 6 such segments and pays close attention to creating holistic solutions for these developers. The first of these segments is performance 3D graphics on desktop and mobile devices that have many years used the Khronos OpenGL and OpenGL ES APIs, and now the industry is moving to the new generation Vulkan with Sphere V enabling significant innovation in shading and language kernel compilers. The embedded industry can use the same desktop GPU APIs, but has also created safety-critical versions of both OpenGL and Vulkan to ease system safety certifications. The embedded computation market can use those GPU APIs for GPU acceleration, but it has also evolved general-purpose compute-only APIs such as OpenCL and SYCL, and vision and inferencing acceleration frameworks such as OpenVX. Applications needing access to high-performance compute on desktop and supercomputers may use OpenCL or SYCL, which is often layered over OpenCL, with Inari used to visualize simulation results. Both compute and graphics applications often need access to pervasively available 3D assets held in the Gltf file format, with WebGL making 3D rendering available in any browser, with the emerging area of 3D commerce leveraging both of these standards. And finally, augmented and virtual reality applications are a good example of where Gltf 3D assets are vital together with Vulkan and WebGL, enabling XR graphics rendering natively or in the web, together with Openxr, providing portable access to HMD displays and devices. As Khronos works to create these open standards to meet industry needs, it consistently adheres to a number of core principles. Firstly, Khronos membership is open, and any member is welcome to join at any time for a full voice and a vote in how any Khronos standards evolve. Secondly, Khronos works hard to ensure its standards are responsive to real industry needs by enabling proposals for new standard initiatives to come from any company, whether or not they are members, and focusing resources on standards that become widely adopted. Organizationally, Khronos has an effective IP framework that provides strong protections for members' IP, but also enables royalty-free industry standards through members agreeing that they will not assert their patents against conformant implementations of standards that they have helped to create. Khronos invests significantly in conformance tests, as they are vital as the specification itself to define a true standard that can be reliably implemented by multiple adopters. And finally, Khronos is a non-profit organization where all membership and adopters' fees are used to fund Khronos activities for the benefit of the industry. Internally, Khronos creates a working group to manage and evolve each of its standards, and all members are free to join as many working groups as they wish. Many working groups have advisory panels of invited industry experts to provide requirements and feedback on specification drafts. The Khronos board is made up of companies that pay a higher membership fee and are motivated to help set the strategic direction for Khronos, including how Khronos directs its budget. Each working group has a number of worked products. The specification and associated conformance tests enable adopters to correctly implement the specification. Adopter programs enable those implementers to submit their conformance test results for working group approval. Tools, developer samples, educational materials, and sample implementations are often released into open source for industry feedback and participation. So that was a very quick high-level Khronos overview. These slides and much more information are available on the Khronos website. Khronos is committed to play a vital role by providing a safe space for companies to cooperate to create open standards that benefit their own business and the wider industry. Joining Khronos provides significant benefits to all its members, such as industry networking and getting early insights into industry trends and the chance to influence those trends. Early access to draft specifications enables you to bring your products faster to market. If your own company is using Khronos standards and would like a voice and a vote in how these standardization activities evolve, or you wish to use or implement any Khronos standard on your device or platform, Khronos warmly welcomes any company that wishes to participate. We look forward to working with you. Thank you. Hi everyone, I am Neil Trevitt. I work on developer ecosystems at NVIDIA and I am president of the Khronos Group. And I'm going to give you a summary and an update on Gltf, which is not an API, but it is instead an open standard file format designed for the efficient and reliable transmission of 3D assets to applications and engines wherever they are needed. The genesis of Gltf at Khronos was the realization that all the major media types, images, audio, video, all had formats designed for efficient and compact distribution, apart from 3D graphics. And those efficient transmission formats had created significant market opportunities, and that 3D was really missing out. So Khronos designed the Gltf 3D asset format to be focused on being compact and easy to process, so it could become widely adopted. And so we call Gltf the JPEG of 3D, as it is the last mile JPEG equivalent that lets you easily transport and deploy and use your 3D assets wherever you need, including in this PowerPoint presentation. Gltf is flexible. It can describe any 3D model from single objects to full scenes with animation. It is a pure asset format that can be used in any runtime or application. Gltf is also extensible, enabling it to efficiently evolve to meet new use cases. Gltf 1 was designed to be used directly in WebGL and so used GLSL shaders to define materials. WebGL 2 significantly broadened the adoption of Gltf by defining physically based rendering or Pbr materials that are both visually compelling and can be processed by any 3D graphics API on any system. Gltf uses JSON to describe the 3D scene hierarchy and uses binary payloads to describe geometry, animations, and skins. Textures are included as JPEG, PNG, or KTX files. Gltf also uses textures to define its PBR or physically based rendered materials, using textures to map how metallic or rough the materials are or how specular and glossy. This results in very realistic looking objects that can still be rendered very efficiently even on mobile devices and even in a PowerPoint presentation, as we are seeing here. Support for GLTF is now widespread throughout the industry as companies realize the efficiency and cost savings of having tools, apps, and engines that can all communicate assets easily to each other. The companies shown here have all implemented GLTF support, both in tools that generate GLTF assets and engines and applications that ingest those GLTF models. If your company supports GLTF and your logo isn't here, please do let us know. We would love to add it on. GLTF is an extensible standard to enable it to evolve to meet industry needs, and one of the most widespread developer needs, of course, is for small, compact asset file sizes. The Draco Mesh compression extension uses compression technology developed by Google to enable geometry in a GLTF file to be compressed, typically by a factor of 10 to 25 times. Generating and importing Draco compressed GLTF assets is now widely supported by the major 3D tools and engines with encoders and decoders in open source. But of course, for the smallest asset file sizes, we need compressed textures as well as compressed geometry. And unfortunately, the GPU-accelerated texture landscape is highly fragmented, which can make it tricky for developers with portable applications to know what texture formats to pack into their GLTF assets. Today, developers often need to send multiple copies of textures, which increases file sizes, or send textures in image formats such as JPEG that are small in size but take significant processing and memory to convert to accelerated compressed texture formats that are understood by GPUs. The good news is that Khronos is very close to finalizing the definition of GLTF universal textures. They use basis universal compression technology from a company called Binomial to define super compressed formats that enable small file sizes for transmission and can be efficiently transcoded into the preferred accelerated texture format on the destination device. So for the first time, a GLTF file will be able to include a single optimized set of textures that can be easily unpacked into high-quality GPU-accelerated textures for any device. Universal textures use version 2.0 of Khronos' KTX texture container format to hold the basis universal super compressed textures with precisely defined access to all aspects of the textures, including bitmap levels. And providing portable access to bitmap levels enables applications to implement things like level of detail streaming for textures from any source, for example, by transmitting the smaller bitmap levels first for faster download responsiveness. An important property of universal textures is that they are transcoded on the fly into GPU-accelerated texture formats, so textures never need to be stored as fully decompressed intermediate images on the GPU, as you would need to do when unpacking and re-encoding JPEG or PNGs, and this saves a significant amount of GPU memory. This means that universal textures really give you the best of all worlds, smaller than JPEG assets for transmission, easy transcoding directly into a wide range of GPU texture formats with no intermediate file size image buffer. Another very active area on the GLTF roadmap is a new generation of Pbr extensions that add additional material parameters to GLTF's existing Pbr definitions, with the first three being clear coat, transmission for transparent materials, and sheen, and those three are already released. These extensions are being designed by a pretty amazing group of industry experts from Khronos member companies who are guiding the GLTF standard to an optimal sweet spot between materials with very high visual realism, but also can be widespread deployed, even on mobile devices. Beyond these first three extensions, the GLTF working group has received requests to support an even wider range of Pbr parameters listed here. We will be working on these during the first half of 2021, and so if you have any input or feature requests, please go to the GLTF GitHub where these extensions are being openly discussed. We would love to get your input. And even though the first wave of new generation Gltf Pbr materials have just been released, there is already wide industry support, including tools to author the Pbr materials and a widening selection of viewers, engines, and applications that can display these highly realistic models, including Khronos' own open source sample viewer. Khronos has also upgraded its open source Gltf validator to check for valid Pbr materials and has released a set of samples using the latest Pbr materials on GitHub. So that's a very high-level overview of Gltf. I hope you found it useful, and I hope you're inspired to try out Gltf for your next 3D project if you haven't already. We have put some links to Gltf resources here, and all of these slides and more are on the Khronos website. Thank you for your time. Hi, everyone. I am Neil Trevitt. I work on developer ecosystems at NVIDIA. I am president of the Khronos Group, and I also chair the OpenCL working group. I'm going to spend a few minutes giving you a summary and an update on the OpenCL open standard for parallel programming. OpenCL is used to accelerate applications by running them across heterogeneous processors, multiple processors of diverse types, including CPUs, GPUs, DSPs, and FPGAs. There's increasing industry interest in parallel processing acceleration to combat the end of Moore's law, as processor frequency scaling gives way to parallel programming as an effective way to deliver needed performance. Khronos has multiple standards for parallel computation. SYCL and OpenVX shown here are high-level programming frameworks. SYCL enables parallel programming using standard C++, and OpenVX uses a graph abstraction to express vision and inferencing functionality. SYCL and OpenVX may be accelerated by lower-level APIs from Khronos that include Vulcan for programming GPUs and OpenCL that lets you program almost any type of processor. Both OpenCL and Vulkan can process the shaders and kernel programs in Khronos' Pbr standard intermediate representation, which enables significant language and compiler ecosystem flexibility, as we will see a little later. OpenCL is a runtime and programming framework that includes C and C++ based languages for creating compute-intensive kernels that can be compiled and executed across any available parallel processors in a system. OpenCL provides APIs to discover accelerator devices, compile kernels for selected devices, execute those kernels with explicit control over kernel placement, memory allocation, and synchronization, and finally gather the results. When deciding between OpenCL or GPU APIs such as Vulkan, many developers that don't need graphics rendering find that OpenCL provides a simpler programming model, a lighter weight runtime, and more rigorously defined numerical precision that can be critical for many compute applications. OpenCL is the most pervasive cross-vendor open standard for low-level parallel programming. OpenCL is deployed by GPU, DSP, and FPGA vendors and used by an increasing number of applications, engines, and libraries, as well as acting as a back-end target for languages, compilers, and machine learning stacks that need a portable API to reach into hardware acceleration, including Khronos' own SYCL and OpenVX. In particular, almost all mobile inferencing engines from companies such as ARM, Qualcomm, Intel, VeriSilicon, Synopsys, TI, Xiaomi, and others use OpenCL as an acceleration backend. Another indication of how widely OpenCL is used throughout the industry is that there are now over 12,000 open source projects on GitHub using OpenCL. That's a tripling in the last 4 years. One of the most topical and significant open source projects right now, of course, is Folding at Home, being used to research the coronavirus. Folding at Home uses OpenCL for GPU acceleration in its network of consumer PCs, which is now delivering an amazing 2.4 exaflops faster than the top 500 traditional supercomputers combined. The latest version of OpenCL is OpenCL 3 that was released in September 2020. OpenCL 3 enables hardware vendors to focus their resources on driver functionality that their customers really need by making all functionality beyond OpenCL 1.2 optional through API queries and language macros. OpenCL 3 also removed the OpenCL C++ language from the specification and recommends instead using the C++ for OpenCL open source front-end compiler that generates SPIR-V code. Existing applications can be easily moved to OpenCL 3. OpenCL 1.2 applications require no changes, and OpenCL 2.x applications also require no code changes if all the functionality that they use is known to be present. To ensure future portability, though, to any OpenCL 3 implementation, developers are encouraged to query for any optional functionality that they use. Several new extensions were released alongside OpenCL 3.0, including asynchronous DMA extensions that enable DSP-like embedded processors to transfer data between global and local memories via DMA transactions. This new functionality complements previous one-dimensional operations by supporting complex memory transfers and use of fences for synchronization of multiple asynchronous transactions running in parallel. There is significant interest in the working group in continuing to extend OpenCL functionality for DSPs and other types of embedded processors. Another set of extensions being actively developed is external memory sharing to enable OpenCL to interop with other APIs such as Vulcan by importing handles to memory and semaphore objects, and then using semaphores to wait and signal the other runtime to coordinate use of the shared memory. Interop between OpenCL and Vulkan will be widely used on both mobile and desktop platforms and will be extended to other desktop APIs in the future, such as DirectX 12 for Windows 10. As an example of OpenCL's growing usage in the mobile industry, Google recently announced a port of TensorFlow Lite to OpenCL to complement its existing OpenGL ES backend. The OpenCL port delivers twice the accelerated inferencing performance on the same devices and over 4 times the performance of unaccelerated inferencing. Even though not officially exposed as part of the Android platform, OpenCL is often provided by mobile GPU vendors, and it is increasingly being used as an acceleration target for mobile inferencing frameworks as well as video and imaging libraries. OpenCL is also used as a back-end target for many machine learning compilers to harness inferencing acceleration. Many companies are researching and developing machine learning compilation stacks. For example, Amazon with TVM, Facebook with Glow, and Google with XLA. All these compiler stacks follow a similar pattern. Firstly, import a trained network, then apply graph-level optimizations to that network, and then decompose the network into executable instructions. All these machine learning compilers can emit OpenCL code to portably access parallel hardware acceleration, illustrating how OpenCL is the most pervasive, close-to-metal execution layer for machine learning libraries, engines, and compilers. As GPU and parallel acceleration solutions become increasingly dependent on this type of compiler technology, SPIR-V is becoming an ever more important part of the Khronos standards ecosystem. SPIR-V is an intermediate language representation that includes heterogeneous parallel processing and graphics operations that can be broken down into instructions for GPUs and other processors. SPIR-V is the only language directly ingested by Vulkan, and it can be imported into a growing number of OpenCL implementations. SPIR-V enables the hardware and compiler communities to innovate independently, as front-end compilers can simply generate SPIR-V code to be ingested and executed by a wide range of runtime APIs. In addition, API runtimes that ingest SPIR-V eliminate the need for front-end compilers to be deployed in embedded systems. Next, I want to talk about the growing industry trend of layering APIs over other APIs through the cross-compilation of shading languages by this increasingly robust open source compiler ecosystem leveraging SPIR-V. For developers, a layered API can enable their application to run on platforms that don't support that API natively. For example, the Google CLSPV compiler enables OpenCL kernels to be compiled and executed on a Vulkan runtime, which, together with the CLVK runtime API translator, enables OpenCL applications to run over Vulkan. CLSPV is already being used to ship demanding OpenCL applications on Android, such as Adobe's Rush video editor that has over 200,000 lines of OpenCL-C running on Vulkan with full GPU acceleration. Layered APIs can also be invaluable to platform vendors as well as developers to enable content on a platform without incurring the support load of an additional kernel-level driver. For example, Microsoft is working on the newly announced OpenCL on 12 open source project to layer OpenCL over Microsoft's own DX12 API. OpenCL on 12 leverages the Mazer open source graphics framework, and Microsoft is working together with Collabora to enable OpenCL wherever Windows 10 ships, including on ARM-based PCs and in the cloud. So that's a overview of OpenCL 3.0 in a nutshell. I hope you found this to be a useful overview. We have put some links here to OpenCL resources, and all of these slides and more are available on the Khronos website. For example, the working group has placed the specifications and conformance tests in open source on GitHub to enable bug fixes and suggestions from the community. And any feedback is also welcome on the Khronos forums. Thank you for your time.
네, 다음 발표는 슈리닉 샤들기 3D 커머스 워킹그룹 의장께서 발표해 주시겠습니다. 슈리닉 샤들기 박사님은 웨이페어의 엔지니어이시고요. 그 다음에 3D 커머스 그룹은 3D 상거래에 필요한 3차원 어셋과 가이드라인 그리고 인증 관련된 표준을 제정하고 있습니다. 샤들기 박사님은 콜롬비아 대학에서 컴퓨터 사이언스를 전공하셨고 그 다음에 MSTA의 펠로우십을 갖고 계신 엔지니어가 되겠습니다.
Hi everyone, welcome. Thanks for taking the time and thanks for joining us today. My name is Shrenik Sabagi and I'm the chair of the 3D Commerce Working Group. In my day job, I work for Wayfair, where I lead a small team that is trying to figure out the future of retail and home by investigating emerging technologies. But today, I'd like to talk to you about 3D commerce, why we are here, why we created the group, and what our goals are. When you think of merchandising and the way it's evolved, we've gone from text descriptions of products to images that represent products to now 3D. I believe 3D is a medium that is very impactful for merchandising, especially when you think about the visual computing technologies such as augmented reality and virtual reality, where you can let customers place products in their space or immerse them in virtual environments and have them engage with your product and your brand in a more meaningful way. Before we can see widespread adoption of 3D in retail, there are a few hurdles that we need to overcome. And let me try to illustrate this with some examples. So let's take search as a use case. Google just announced support for 3D and AR search. Now, what that means is you could search for a product and actually see it, engage with it in 3D and place it in your space and then purchase it. And there are many experiences like this where 3D is becoming a lot more powerful in the discovery process. So imagine this across multiple platforms now. Because of the inherent rendering capabilities and the differences in the underlying platforms, to an end user, this chair is going to look a little different across different platforms. Visually, it is not going to be consistent. There are going to be small, slight differences. That leads to a poor customer experience, where the customer does not know which specific platform is the best one to use in order to perceive the product correctly. So that's one problem, and that's on the end user side of the spectrum. But where does this content come from? How do you produce this asset in the first place? What are the problems in that part of the world? So as an example, a manufacturer who wants to sell a product relies on either a retailer or a shopping platform to actually help them sell the product. The retailer or the shopping platform usually employs a team of content creators or employs a service of content creation, where a team of 3D artists then use 3D tools to actually produce the 3D content. So you can see that there are multiple actors and multiple roles that people are playing in multiple organizations to actually produce content. So when you zoom out a little bit and take a holistic view of the entire supply chain and this pipeline of how a product gets created and how it's finally displayed or experienced on a device, multiple people have different definitions of what a virtual product is. And we need to, the problem with that is that as content exchanges hands, that definition changes. And people need to create or recreate assets based on different definitions. This workflow would be a lot more streamlined if we all aligned and actually agreed on what a virtual product is, what constitutes a virtual product, and what defines a virtual product. And that's one of the reasons why 3D Commerce was created. Our mission is to create specifications and guidelines to help with this asset workflow, all the way from product design and manufacturing to the end customer experience. In a simpler way, we want people to be able to create virtual products once in an easy way and have them be able to reuse it across different platforms without having to worry about how that product would look, how people would experience that product. A content creator should have confidence in what they're creating. Will that product withstand time, and will it withstand multiple platforms? Does it have the longevity to do that? That's what we are trying to do. That's the mission. So trying to break that down into the sub-problems, the first one that we're trying to tackle is achieving that visual consistency across platforms. A virtual product should look the same when you see it across different platforms. That's critical to provide a good, consistent end user experience. When you think of products come in multiple shapes, sizes, and colors. But how do you package all that stuff up? How do you do that intelligently so that you can, the content creator can actually do it in an easy way, in a very well-defined way that works well across multiple platforms and can get distributed over the internet and over the wire to the end user devices. Currently, there's no way of doing that. So we plan to create one. And that's one of the goals of 3D Commerce as well. When you think of information about the product, where does that information lie? Should that be embedded inside the product, inside the 3D model, or should that be separate? What kind of information should be embedded in the 3D model? So we're trying to figure out answers to these questions. Metadata like description of products, the names of the products, something as simple as that. Something more semantic, like where does the product attach to the physical world? What I mean by that is, how does a product interact with the physical world? So for example, a couch, does it sit on the floor? Does a chandelier hang from a ceiling? Does a wall sconce hang from the wall? Things like that, where we're trying to figure out how do we embed that kind of information into the 3D model itself. And last of all, how does someone produce this content in the first place? How do we educate everyone to ensure that people are creating content in a streamlined way that's not wasteful and that's a lot more efficient? In fact, we have released the first version of a set of asset creation guidelines that would help content creators create an efficient asset that would work on multiple platforms. So here's a set of problems that we're trying to tackle as in the short term. And as the group evolves and as we tackle some of these problems, we will take on a different set of problems. And that's where we need your help. We want you to be involved in this effort, especially if you're in the 3D commerce ecosystem, if you're a content creator, if you're a developer, if you're a DCC tool provider, if you are a manufacturer, a retailer, a technology platform, if you're involved in anything to do with retail and 3D technologies, you should be involved. So check out the website, go to khronos.org/3dcommerce, send us an email, 3dcommerce-feedback@khronos.org to be involved. And definitely check out the first version of our real-time asset creation guidelines. There is a QR code on the screen here. Please try to follow the link and give it a read and let us know what you think. It's a living document that we've hosted on GitHub, and we expect, we would love your feedback on it. We believe that with your help, we can refine the document to a point where it can be broadly distributed and be followed and lead to more streamlined and efficient asset creation. Our goal that you see on the right here is render everything everywhere. I'll end with that. Thank you so much for your time.
예, 다음 발표는 AR, VR 관련된 표준인 OpenXR 표준에 대해서 블랜드 잉스코 오픈XR 워킹그룹 체어가 발표를 해주시겠습니다. 블랜드 잉스코 박사님은 노스캐롤라이나 대학 채플힐에서 박사를 하셨고요. 현재는 인터넷 게이밍 담당 엔지니어로 활동하고 계십니다. 오픈XR 워킹그룹에서 의장을 맡고 계시면서 동시에 20년 이상 3D 그래픽 프로그래밍 관련된 엔지니어링 경력을 갖고 계십니다.
My name is Brent Insko, and I'm lead XR architect at Intel and the working group chair for OpenXR. I'll start by discussing what OpenXR is, why we needed yet another standard, and where we are today. OpenXR is a royalty-free open standard that provides high-performance access to augmented reality and virtual reality platforms and devices. As a note, I'll be using the term XR throughout the talk, which include AR and VR and MR and any other similar technologies. OpenXR handles communication to and from an application and an XR platform or device. An XR platform provides the application information such as the head and hand position information about the controllers and the input state such as whether a button has been pressed or released, and also display configuration and form factor information such as whether there is a single display or multiple displays. The application provides the XR platform an image or images to display, audio, and also haptic responses, such as vibrational responses in controllers. Before OpenXR, an application developer would have to program each platform's proprietary API. This becomes a daunting challenge as you support more platforms, both from a development perspective, but also a validation and testing perspective. OpenXR enables application developers to program to a single, common, high-performance API, which supports a number of different AR and VR platforms. OpenXR contains everything an application needs to drive XR devices in a system, including device discovery, event processing, sensor tracking, and pose calculations on the input side, and frame display timing and composition, plus haptic controls on the output side. OpenXR is used alongside a rendering API such as Vulcan to generate imagery. OpenXR can be used with any 3D API, but a new generation API such as Vulkan is particularly well suited to create applications with high rendering performance and a low latency that are so vital for a compelling XR experience. So this is a high-level overview of a possible OpenXR application, and it's just to give an example of the flow of the program and the steps involved. We don't have time to get into the details today, so I encourage you to check out our GitHub repository and member company sites for sample code to start from. This July, we gave a one-year update after the release of the 1.0 specification at SIGGRAPH last year. We have launched the OpenXR adopter program and open sourced the conformance test suite on GitHub. We have a number of OpenXR conformant platforms and additional developer preview implementations. And we have also released hand and eye tracking extensions for advanced user interfaces. So now I'll talk briefly about the latest developments with OpenXR. In October, Unity announced upcoming OpenXR support by the end of the year on partner platforms, with further support coming early next year for all conformant OpenXR 1.0 runtimes. Also in October, the Blender Foundation, the organization behind Blender, the free open source 3D creation suite, has joined Khronos. This enables them to help shape the future of OpenXR, Vulkan, Gltf, and many other Khronos APIs. We also have two new conformant implementations. We have the Oculus Quest 2 and the HTC Vive Cosmos. Given a current implementation status update, we currently have conformant implementations including the Microsoft HoloLens 2 and all Windows mixed reality headsets. For Oculus, we have the Rift S on the PC, as well as the Quest and Quest 2 all-in-one devices, and we have the HTC Vive Cosmos. For developer preview implementations, we have Valve with a preview implementation on Steam VR. We have Vario with their various headsets, and we have an open source implementation named Monado, provided by Collabora. With these initial conformant devices, we can really show off the flexibility of OpenXR. We have devices that cover both AR and VR. We have devices that are tethered to a PC, as well as all-in-one devices. And we have devices that support Android as well as Windows. By the end of the year, OpenXR will have wide support across game and rendering engines. Unreal Engine has supported OpenXR since last year and has since released improvements around performance and mixed reality capture. Blender has supported OpenXR since its 2.83 release in June, using OpenXR for VR scene inspection. And as mentioned earlier, Unity support is coming very soon. It's still early days for game support for OpenXR, but Microsoft has announced that Minecraft's new Render Dragon rendering engine is building its desktop VR support on OpenXR. OpenXR has been integrated into Chromium, the open source browser project, and with release 81, OpenXR is the default backend for WebXR support. This enables Google Chrome and Microsoft Edge browsers to use any OpenXR compatible device. We've also released, as I mentioned earlier, cross-vendor OpenXR extensions for advanced user interfaces, including hand tracking and eye tracking. And to give a bit more detail on the OpenXR hand tracking extension, it's a multi-vendor extension which enables applications to render fully articulated hands in XR experiences and to use these virtual hands to interact in XR. It includes all the major hand tracking solution providers in XR on the same standard and includes support for a wide range of hand tracking technologies, such as optical hand tracking from Ultraleap, Oculus, Magic Leap, and HoloLens, as well as controller-based hand tracking, such as the Valve Index and Oculus Touch controllers. There is also an experimental overlays extension. This extension allows overlays apps to insert their content into another application's world. This extension was added to Openxr in version 1.0.8. Developers who want to test out overlays and provide feedback regarding the extension can try it out on Collabora's Monado on Linux, or download the work in progress API layer from LunarG and Pluto VR on Windows. LunarG has made the API layer source available on GitHub. We also mentioned briefly earlier the developer preview implementations, and one of which is Monado. Monado is a fully open sourced permissive license provided by Collabora and community. It's currently passing conformance, though it's not yet a fully conformant implementation, and it supports overlays and has Android support. We also have member companies helping to advocate for Openxr. Holochip is creating a set of resources for Openxr developers, which will be accessible on their website. The resources will cover the basics of setting up an application, the Openxr development environment, including the Openxr SDK, runtime, device driver, and a sample application. It will also cover modifying the runtime functionality, such as the SLAM implementation, and creating Openxr extensions. Holochip also offers consulting services in support of Openxr. So now is the time to get involved with Openxr. Khronos has open sourced the conformance test and launched the adopters program. We have officially conformant runtimes from Microsoft, Oculus, and HTC. We have preview implementations from Valve, Vario, and Collabora. We have hand and eye tracking cross-vendor extensions for advanced user interfaces and the experimental overlays extension. And Openxr is being used by real software today. We have Unreal, Blender, Chrome, Edge, and soon Unity and Minecraft support. Thanks, and visit our website for more information.
다음 발표는 벌칸에 대해서 톰 올슨 벌칸 워킹그룹 의장이 발표를 해주시겠습니다. 톰 올슨 박사님은 유니버시티 오브 로체스터에서 컴퓨터 사이언스로 박사학위를 받으셨고요. 그 이후에 유니버시티 오브 버지니아의 교수님으로 계셨습니다. 그 이후에 산업계로 옮기신 후에 현재는 ARM의 GPU 관련 기술의 수석 엔지니어로서 일을 하고 계십니다.
Hello, my name is Tom Olson. I work for ARM and I'm chair of the Vulcan Working Group. I'm here to tell you about what's been happening in Vulcan over the past year. But before I do that, I want to say a word or two about what Vulcan is. Briefly, Vulcan is a modern cross-platform API for high-performance graphics and compute using GPUs. It gets its hardware model from OpenGL and OpenGLES, and its architecture and design philosophy from AMD's Mantle. What does that mean? Well, a traditional API like OpenGL presents you with a very high-level abstraction that does not look very much like the underlying GPU. To make that work, you have to have a large, complex software driver to do things like memory management, synchronization, error checking, high-level shading language compilation, and so on. It's convenient for the application, but there are problems. The driver uses a lot of CPU cycles. It's hard to understand and it's hard to optimize for. And because the driver doesn't know what the application is trying to do, it is often unable to make good decisions about how to do it. In Vulkan, on the other hand, you get a very thin abstraction, which looks very much like the underlying hardware. Most of the complicated functionality moves out of the driver. Shading language compilation moves offline. Error checking moves into separate optional validation layers, which you use only at development time. And memory management and synchronization move into the application. That's more work for the application, but because the application knows what it's trying to do, it can often do a better job than the driver could. And because the driver is simple, it's easy for the application programmer to predict how the driver will behave. Vulkan has been shipping since 2016. It's available now on a wide variety of desktop OSs, platforms, consoles, etc. There's a lot of great AAA content shipping on it. In mobile, Vulkan is available on essentially all high-end premium Android devices, and there's great content shipping there as well. So that's what Vulkan is. Now I'll talk about new functionalities since last year. Only the highlights. There's more than I can talk about today. So we released Vulkan 1.2 in January. As usual, we created Vulkan 1.2 by bundling together a number of extensions created earlier. And since that functionality is really more than a year old now, I won't say much about it. I do want to point out that a lot of effort went into making Vulkan 1.2 work really well with HLSL as a first-class shading language. A lot of developers told us that they prefer to write their shaders in HLSL, and we heard them and responded. You can, of course, still use GLSL as you always could. There's lots of other good technology in Vulkan 1.2, and it gives us a good foundation for the future, but I don't really have time to talk about it today. Thank you for your time and attention and for the work that you do. I look forward to seeing the amazing things that you are going to do with Vulkan.
네, 다음 발표는 데니엘 컥인데 벌칸 레이 트레이싱 서브 그룹 체어이십니다. 데니엘은 유니버시티 워털로에서 수학 학사를 하셨고 그다음에 컴퓨터 사이언스로 마스터 학위를 받으셨습니다. 그리고 지금 현재는 엔비디아의 3D 그래픽스 팀의 모바일 3D 그래픽스 팀의 엔지니어로 그래픽스 관련된 연구를 계속하고 계십니다.
Well, speaking of doing amazing things with Vulkan, I'm here to talk to you about ray tracing in Vulkan. Hi, everyone. I am Daniel Koch, and I work on graphics drivers at NVIDIA and am the chair of the Vulcan Ray Tracing subgroup at Khronos. The Vulcan Ray Tracing subgroup was formed in early 2018 and was tasked with bringing a ray tracing solution to Vulkan. In March 2020, the provisional ray tracing extensions were released to gather public feedback and input into the final design of these extensions. In November 2020, the final Vulkan ray tracing extensions were released, and shortly after that, in December, the Vulkan 1.2.162 SDK was released, incorporating support for these extensions and enabling developers to easily integrate Vulkan ray tracing into their applications. The ray tracing subgroup received a number of design contributions from hardware vendors and examined requirements from both software and hardware vendors. Real-time techniques for ray tracing are still being actively researched, and so the first version of Vulkan ray tracing has been designed to provide a framework while setting an extensible stage for future developments. One overarching design goal was to provide a single coherent cross-platform and multi-vendor framework for ray tracing acceleration that could easily be used together with existing Vulkan API functionality. Software vendors were also clear. We needed to enable content design for contemporary proprietary APIs such as NVIDIA's OptiX or Microsoft's DirectX ray tracing to be easily portable to Vulkan. As such, we use a familiar overall architecture, including enabling the reuse of HLSL shaders, while also introducing new functionality and implementation flexibility. We've enabled selected parts of the framework to be optional for deployment flexibility in keeping with the Vulkan philosophy. For this first version, we are primarily aiming to expose the full functionality of modern desktop hardware, but in a way that is hardware agnostic and can be accelerated via existing GPU compute or dedicated ray tracing cores. So how do you use Vulkan ray tracing? Like many other ray tracing APIs, the first step is to build the scene geometry into an efficient two-level acceleration structure so that searching for ray tracing intersections can be optimized. The precise internal organization of the Vulkan acceleration structure is opaque to the application so that the hardware vendor can optimize it to match their own architecture. The KHR acceleration structure extension provides the ability to create and build acceleration structures on the GPU or optionally on the host. more about that later. It also provides acceleration structure management commands, which enable compaction and serialization of acceleration structures. An acceleration structure is a highly optimized implementation-dependent data structure that is built from the application-provided scene data and placed in a buffer. This opaque data structure is used to achieve high-performance ray intersections in complex scenes. The acceleration structure is divided into a two-level hierarchy, as shown. The bottom-level acceleration structure contains triangles or axis-aligned bounding boxes of custom geometry that make up the scene. Since each bottom-level acceleration structure may correspond with what would be multiple draw calls in the rasterization pipeline, each bottom-level acceleration structure can contain multiple sets of geometry of a given type. The top-level acceleration structure contains references to a set of bottom-level acceleration structures. Each reference includes shading, transform information for that reference. The bottom-level acceleration structure is only used by reference from the top-level acceleration structure. The top-level acceleration structure is accessed from the shader as a descriptor binding or by device address. Next, we need to launch rays into the scene to determine how those rays intersect and interact with scene geometry, materials, and light sources, and to process those intersections with programmable flexibility to enable a wide variety of visual effects. Vulkan provides two ways to traverse the scene. The first method, shown on the bottom left, uses the new ray tracing pipeline that enables the application to compile a set of shaders into a pipeline to handle any desired ray and material processing, and then launch a grid of rays into the scene with the ray tracing pipeline invoking the appropriate shader when intersection occurs, or a miss shader if no hits occurred for that ray. The second technique to fire rays, called ray queries on the bottom right, is much more explicit and enables any type of shader to launch a ray at any time and process the intersection data however it wishes. This is a very flexible technique, as the shader also controls how the traversal proceeds through the scene, but it does place more burden on the shader author. The KHR Ray Tracing Pipeline extension adds the new ray tracing shader stages, pipelines, and associated commands. The corresponding SPIR-V KHR Ray Tracing and GLSL X Ray Tracing extensions define the associated SPIR-V and GLSL constructs. Ray tracing pipeline work is launched using VK command trace rays KHR. This command invokes an application-defined set of ray generation threads, which can call trace rays X from the shader, starting traversal work on the specified acceleration structure. During traversal, if required by the trace and acceleration structure, application shader code in intersection and any hit shaders can control how traversal proceeds. After traversal completes, either miss or closest hit shader is invoked. The different shaders can communicate parameters and results using ray payload structures between all traversal shaders and hit attribute structures from the traversal control shaders. To enable the traversal phase to know which shader to invoke after a given step of traversal to control or respond to the traversal, the implementation uses a shader binding table. Each shader entry in the table consists of a shader group handle plus an optional shader buffer record, which the application may use for instance-specific data such as buffer device addresses or descriptor indices. The address for any given shader is computed by the traversal through a combination of parameters to the trace rays API call, parameters to the trace rays shader call, and information stored in the acceleration structure. The KHR Ray Query extension enables ray queries for all shader stages, including graphics, compute, and ray tracing shaders. The corresponding SPIR-V KHR Ray Query and GLSL X Ray Query extensions define the associated SPIR-V and GLSL constructs. Ray queries can be used to perform ray traversal and get a result back in any shader stage. Other than requiring acceleration structures, ray queries are performed using only the new shader instructions. Ray queries are initialized using ray query initialize, which specifies an acceleration structure to traverse and various properties of the ray being traced. Next, ray query proceed is used to start the traversal. After an intersection candidate is found, the shader can examine properties of the potential intersection and of the ray itself using instructions which are accessible to shader during traversal and specify how the ray should be handled, either by generating intersection details, confirming a hit, or terminating the ray. If the traversal is not finished or the ray terminated, ray query proceed can be called again to continue the acceleration structure traversal. A ray tracing application can use hundreds or even thousands of shaders to process the many types of visual effects in a scene. Compiling that many shaders into a ray tracing pipeline can be intensive enough to cause application stuttering when new scenes are loaded or when new scene effects are needed. It can be particularly aggravating to discover that a scene suddenly needs a new shader, and that triggers the entire set of shaders being recompiled and reloaded. To avoid that overhead, the KHR pipeline library extension enables a library of SPIR-V shaders to be incrementally compiled into an existing ray tracing pipeline, saving the need to recompile everything from scratch. A pipeline library is a pipeline which includes the normal state and shaders, along with an additional flag to indicate that is not intended to be bound directly to the API, but is intended to be used as a library that will be linked with a later pipeline. Pipeline libraries can also be included in multiple ray tracing pipelines, allowing shader compilation results to be reused across pipelines. Ray tracing pipeline creation may include both pipeline libraries as well as additional ray tracing shaders directly. All of the compilation state from each pipeline must match to successfully create the final linked program. Pipeline libraries can be helpful when dynamically managing shaders in a scene, but there is still significant setup processing for any ray tracing application, not just compiling shaders, but also loading geometry into acceleration structures. To help applications use all the available processors in a system for scene setup, we have provided the ability for the host CPU to build acceleration structures in host memory for subsequent download to the GPU, enabling the host CPU to perform setup in parallel with the GPU performing other work. The KHR deferred host operations extension provides a mechanism where the driver returns a deferred work handle to the application for later execution, enabling the application to control work execution and to distribute the work onto multiple cores and background threads. In a ray tracing application, deferred host operations can be used to asynchronously leverage multiple CPU cores to build host acceleration structures. They can also be used to parallelize ray tracing shader compilation and pipeline generation. So this was just a quick overview of the Vulcan ray tracing extensions that are now available. Production ray tracing drivers for AMD and NVIDIA GPUs are now shipping, and Intel drivers should be available later this year. For more information about Vulcan ray tracing, here are a number of links to blog posts, tutorials, and other resources. Welcome to the era of portable, cross-vendor, cross-platform ray tracing acceleration. We look forward to seeing how you will use it.
다음 발표는 피에르 부디에 벌칸 머신러닝 서브그룹 체어이십니다. 피에르 부디에는 에콜 폴리테크닉 인 파리에서 수학과 물리학에 대한 석사학위를 받으셨고요. 그 다음에 크로노스 그룹에서 벌칸 머신러닝, 벌칸을 이용한 기계학습에 대한 서브그룹의 의장을 맡고 계십니다. 이전에는 엔비디아에서 그 오픈GL 관련된 그래픽 드라이버와 GPU 구조에 대해서 연구를 지금까지 해오고 계십니다.
Everybody has heard about the cool new things that can be done using machine learning, and I'm here to talk to you about how this can be achieved using Vulkan. Hi everyone, I'm Pierre Boudier. I work on graphic drivers at NVIDIA, and I'm the chair of the Vulkan machine learning subgroup at Khronos. This group was formed in spring 2019 and was tasked with bringing a machine learning solution to Vulkan. The machine learning subgroup received a number of design contributions from hardware vendors and examined requirements from both software and hardware vendors. The design goal was to enable the ecosystem with an easy integration with the rest of the Vulkan API functionality. Machine learning is still an active area of research, and new neural networks are coming out every year. While there are a number of natural building blocks like matrix simplification, convolution, rectified linear unit, sigmoid, hyperbolic tangent, there is a combinatory explosion of architectures, as well as new arithmetic concepts being added every week. For instance, locality-sensitive hashing, sparse matrices, quantized weights, binary weights. So software vendors were also clear. There is a need for a solution in the Vulkan ecosystem which has lower overhead than using interop with some other API, and without having to install large external frameworks like Python. Luckily for us, we did not have to start from scratch, as Vulkan already had a compute API capability built in from day one. Additionally, some of the new functionality, specifically targeting machine learning, has some crossover requirements with traditional graphics compute usage. As a result, new extensions were introduced in the initial release of Vulkan that benefit directly machine learning specific workflows. So what does it mean to do machine learning in Vulkan? In a typical workflow, a data scientist will create a neural network by training it on a desktop or in the cloud using high-end accelerator systems. Those networks are then exported using some exchange format, which includes both the definition of the computational graph and the value of the parameters. Two of the formats are NNEF and ONNX, NNEF being defined and supported by Khronos. At runtime, the application would load those formats and generate some compiled code that can be executed in a step called inferencing. The application would use the Vulkan API via compute shaders to offload the computation on the GPU accelerators. So how does one use compute shaders and what precisions should be used? Machine learning is about running a computational graph, which by default is usually done in 32 bits in the Python frameworks. The precision has to match between training and inferencing. There is actually very little difference between training and inferencing from an execution point of view. Training is just running two extra graphs to backward propagate gradients and to update the parameters. For many architectures, it is actually possible to use lower precision than the full 32-bit, which results in both faster execution and reduced data storage. 16-bit floating point can be used by monitoring the magnitude of the gradients during training to avoid 1 to 0 for small values. 8-bit integer can also be used in quantized network, which are generated by distillation phase. Vulkan supports those data natively since the version 1.2 or via the extensions VK-KHR shader float 16 int 8 and VK-KHR 8-bit or 16-bit storage. An upcoming extension, FPV-KHR integer.product, allows to write optimized kernels using integer math without having to rely on compiler optimization. Next, we look into ways to improve Vulkan compute for ML. The first upcoming extension, VK-KHR workgroup memory explicit layout, improve the efficiency of loading data into shader memory without blocking the arithmetic units. The second upcoming extension, VK-EXT-ML primitives, exposes common building blocks that are found in the layer of the popular neural nets, which the driver can then optimize more thoroughly. More details will be shared for those two extensions once they become publicly available. The third extension is already available, VK-NV cooperative metrics, and can be used in a shader to directly access dedicated hardware optimized for matrix simplification. This is typically done for MATMR and convolution layers using 16-bit floating point precision. So how does one get started? An easy way to run your networks in Vulkan is to compile the computational graphs thanks to a generic compiler. We will mention two open source projects. TVM, originally started at the University of Washington, will compile networks into SPAV that can be run on top of the Vulkan API. MLIR is a multiple level IR infrastructure developed inside LLVM, associated with an IR execution engine, IRE, which can generate both SPAV code and the associated Vulkan API code. Looking into more detail of MLIR IRE, Google has been collaborating closely at Khronos when developing the Vulkan-based inferencing solution. The compiler starts from a generic XLA HLO description of the network, which can be generated from the TensorFlow PyTorch Python frameworks. It will then lower successively into lower level of abstractions, each one of them targeting a domain-specific dialect. The last output is a combination of the SPAV code that can be compiled to a specific GPU ISA by the driver and a list of Vulkan API calls in order to submit those kernels and manage the associated allocations and synchronization points. The compiler has a unified view of the entire computational graph and can optimize efficiently across layers and schedule dispatching of operation without unnecessary synchronization. Other third-party frameworks do provide acceleration using Vulkan. Let's have a look at a few. Alibaba provides the MNN library, which can do both inferencing and training on mobile platforms. It is already being used in many of the most popular Alibaba applications like Taobao, Tmall, Youku, DingTalk. Tencent provides the NCNN library that can do inferencing on multiple platforms, mobile and desktop. It is being used by many of the popular Tencent applications such as WeChat, Baidu, QQ, Qzone. Finally, Axe Inc. provides SDK called ILIA, which has highly optimized implementation of many of the popular networks across multiple platforms and provide multiple support options for companies interested in deploying neural nets. There are options to do machine learning with Vulkan outside of purely running neural nets. VKFST is an open source project started by Yuli, which provides highly efficient fast Fourier transform kernels with lots of possible parameterization. It has shown great results for image resampling, image registration, and even in generic signal processing for physics simulation. Compute is a framework that allows writing kernels and algorithms for deployment on multiple vendor graphics cards with integration in both C++ and Python. Finally, Unity provides ML agents, which can be used to train intelligent agents within the Unity game engine based on reinforcement learning, proximal policy optimization, and soft actor critic. So here's our call to action. This was an overview of the Vulkan machine learning capabilities that are now available. Production drivers have been shipping for a while on many devices. We are welcoming feedback from application or framework developers. If you have needs which are not addressed at all by the existing solutions, or if you have pain points which could be alleviated, do not hesitate to contact us. We are interested in both neural net workflows and other classical machine learning algorithms like random forest, logistic regression, TSNE, k-nearest neighbor. My email address is pboudier@nvidia.com. Alternatively, you could decide to join the Vulkan advisory panel or even become a Khronos member. Thank you.
네, 오늘 미리 레코딩 돼서 발표하는 비디오는 지금 여기까지고요. 예, 지금 간단하게 제가 마무리하는 슬라이드 몇 장 보여드리고 그 다음에 설명을 몇 가지 드리도록 하겠습니다. 혹시 질문이 있으시면 채팅창을 이용해서 질문을 해주시면 좋겠습니다. 먼저 설명드려야 될 것이 이제 회원사입니다. 오늘 방문하신 분들 중에 회원 회사에서 오신 경우도 있겠지만 회원 가입을 생각하시는 경우에는 또 상당히 또 우리나라에서 어떤 기관들이 참여하고 있는지 궁금하실 텐데요. 예, 간단히 설명드리면 삼성전자가 참여를 하고 있고, 네, 그 다음에 대학의 경우에는 서울대, 경북대, 그리고 제가 있는 아주대학교가 예, 참여를 하고 있고, 연구기관으로는 애트리가 참여를 하고 있습니다. 그래서 여러분들도 혹시 참여 의사가 있으시다면, 참여하신다면 굉장히 도움이 될 것이라 생각되고, 필요한 것이 있으면 저한테 연락을 주시면 도움을 드리도록 하겠습니다. 표준들에 대해서는 이미 닐 회장님이 요약해서 설명을 해드렸기 때문에 지나가도록 하겠고요. 특별하게 새롭게 시작된 워킹그룹에 대해서 조금 설명을 드린다면 아나리라고 하는 네, 여기 아나리라고 하는 것은 사이언티픽 비주얼리제이션을 위한 새로운 워킹그룹입니다. 그래서 데이터 비주얼리제이션, 그다음에 사이언티픽 비주얼리제이션을 위한 데이터 포맷 이런 것들, 그리고 API가 또 표준화를 하기 위해서 지금 바로 시작됐기 때문에 표준이 이제 얼마나 어떤 것이 나올지는 아직 예상할 수는 없지만 지금 현재 표준의 아이디어들을 모으고 있습니다. 그리고 사실은 크로노스 그룹에 가입하시려고 하는 기관들에서 제일 많이 관심이 있는 것이 도대체 특허가 없는, 그러니까 로열티가 없는 표준이라고 하는데 특허를 어떻게 하냐, 여기 대해서 굉장히 관심이 많으신데요. 일단 표준을 사용하는 데는 특허가 없습니다. 하지만 표준 안에는 특허가 많이 들어있을 수도 있습니다. 예를 들면 회원의 특허가 있다고 한다면 그 회원들 간은 소송을 걸지 않고 회원은 자기의 특허권을 포기한 것으로 간주합니다. 포기를 하지 않겠다고 한다면 자기의 특허에 대해서 공개를 하고 이런 특허가 있으니까 지금 표준을 그런 식으로 만들면 내 특허를 침해하지 않고는 표준을 구현하기가 굉장히 어렵다. 이런 걸 자기가 이제 어나운스를 합니다. 그러면 이 부분을 표준에서 빼야 되겠구나. 또는 그 특허가 있다 하더라도 표준 안에 이걸 넣어 놓으면 예를 들면 다른 방법으로 구현할 수 있는 방법이 많다면 그냥 들어가기도 하죠. 그리고 또 경우에 따라서는 특허를 가지고 있는 회사가 이거 내가 도네이션을 할 테니까 우리 표준에다 넣읍시다. 우리 그렇게 할 수도 있어요. 그런데 이렇게 특허에 대한 IP 프레임워크가 회원들 간에는 작동하지만 회원 바깥에서는 작동하지 않습니다. 그러니까 예를 들면 표준 문서가 무료라고 했으니까 내가 마음대로 구현할 수 있는 것이 아닌가? 그럼 구현할 수는 있는데요. 이때 당연히 회원들이나 비회원들이 가지고 있는 어떤 제3자가 가지고 있는 특허를 침해하시면 안 된다. 이건 기본적으로 아셔야 됩니다. 네. 그리고 제가 좀 간단히 설명을 드려야 될 것이 또 하나가 뭐냐면 이제 Exploratory 그룹, 그러니까 우리말로는 탐색 그룹이라고 하는 것이 있는데요. 탐색 그룹은 뭐냐면 그러니까 ISO나 JTC1에서 하고 있는 그 애드호 그룹이나 스터디 그룹하고 비슷합니다. 정식 워킹 그룹을 만들기 전에 어떤 것을 표준화를 해보는 이제 그런 조사를 하는 워킹 그룹이죠. 그러니까 어떤 요구가 있을 때 이런 부분에 대해서 표준을 만드는 것이 어떨까요? 그런 것에 대해서 제안을 하고 그 제안에 대해서 크로노스 그룹에서 간략하게 논의를 한 다음에 그다음에 그죠? 이 탐색 그룹에서 표준화를 만드는 것이 아니라 무엇은 표준을 만들까, 스코프 오브 워크, 그러니까 작업을 무엇을 할 것인가를 결정해서 제출을 하게 되면 이제 당연히 이제 크로노스 이사회에서 오케이, 이거에 대해서 표준을 개발을 하자라고 결정이 되면 정식 워킹 그룹이 되는 겁니다. 물론 경우에 따라서는 이 과정에서 이거 생각보다는 시장이 너무 작다라든지 이건 우리 영역이 아니다 그러면 정식 워킹 그룹 가지 않고 폐기되는 경우도 물론 있을 수 있습니다. 아까 지금 보도 자료가 하나 나간 게 어제 나간 것이 있는데 크로노스 그룹에서 인베디드 카메라에 대해서 이 탐색 그룹을 새로 만든다라고 하는 저희가 있었습니다. 보도자료가 나갔어요. 그래서 그것에 대해서 질문하신 분이 있었는데 그 부분에 대해서는 닐 트래빗 회장님께서 설명해 주겠습니다. Neil, please explain the camera, embedded camera exploratory group.
Yes, yeah, thank you, Juan. Yes, the embedded camera exploratory group is our latest group. It was announced just yesterday, and we've made it open to anyone in the industry who is interested to develop open standards for integrating cameras and sensors into embedded systems in markets such as automotive, autonomous driving, and robotics. And you don't have to be a Khronos member to join. There's a lot of interest in standards for embedded cameras. We have lots of choices in acceleration APIs. We've covered some of them today, but cameras and sensors used to generate sensor streams into those accelerators are still typically using proprietary APIs. So it's really slow and expensive to use new sensors. And as you've just explained, the exploratory group is not yet defining an API, but we're enabling the industry to come together to see if we can agree what standards we want and where should they be created, maybe Khronos, maybe somewhere else. So for anyone who's listening, if you're interested in embedded camera standards, come to the Khronos website and join up. All the meetings are going to be online. They'll start in a few weeks' time at the end of March, and they're expected to have one week meeting a week for a few months to see if we can create that statement of work. Yeah, and that's a good picture of what we're trying to do. So we have acceleration APIs for driving processors, but no APIs for driving the cameras and the sensors. So that's what we're going to be focusing on. Okay, so back to you, Juan. And thank you for hosting the webinar today.
네, 그러면 이제 크로노스 회원에 좀 가입하는 방법을 안내해 드리도록 하겠습니다. 저희 크로노스 그룹에 가입하기 위해서는 어그리먼트에 물론 당연히 사인하셔야 되고 연회비를 납부를 하시는 방법으로 이제 크로노스 회원을 가입하게 됩니다. 저희가 보시다시피 굉장히 최근에는 새로운 표준화, 특히 뜨는 분야라고 하는 인공지능이나 이런 분야에 대한 표준화가 크로노스 그룹에서 상당히 많이 일어나고 있습니다. 회원 가입을 통해서 내부에서 일어나고 있는 여러 가지 또 새로운 소식들에 대해서 정보를 얻으실 수도 있고, 또 아까 회원에서 보셨듯이 반도체 업체 1등부터 5등까지 다 있고, 폰메이커 1등부터 5등까지 다 있죠. 그런 이제 대기업들의 어떤 액티비티에 대해서도 정보를 얻으실 수 있는 좋은 기회가 될 것이라고 생각됩니다. 상세한 정보가 필요하시면 홈페이지에 문의를 하시면 됩니다. 그리고 혹시 이후에 질문이 있으면 회원 가입에 대해서 member.khronos.org로 이메일을 보내시거나 영어로 이렇게 질의응답을 하시는 게 어려우시면 우리말로 문의를 하시려면 저한테 환영.le 지메일로 문의하시면 제가 답변을 해드리도록 하겠습니다. 그리고 오늘 발표 자료를 제가 유심히 보다가 제가 급하게 저희가 이제 번역을 하거나 또 이제 그 자막 파일을 만들다 보니까 몇 개 오류가 여러분들도 보셨을 것 같습니다. 그리고 또 제가 또 발표자 중에 일부에 대해서 프로필을 잘못 설명한 부분도 있네요. 이런 부분들을 수정해서 이번 주 중에 수정해서 올리도록 하겠습니다. 다음 주에는 저희가 그 파일들을 깔끔하게 정리하고 그 다음에 아까 닐 트래빗의 Gltf 세션이 그냥 캡션이 영어 캡션만 있었는데 그 부분도 제가 번역을 해서 우리말로 번역을 해서 올리도록 하겠습니다. 네, 이게 제가 지금 여기 방송하고 있는 굉장히 복잡스럽죠. 예, 그런데 오늘 1시간 반 동안 여러분들 많은 분들이 참석해 주셔서 너무 감사드리고요. 오늘 수고 많으셨습니다. 감사합니다. Thank you for everyone to participate in this event, and thank you for speakers, and thank you for preparation. And 그리고 이 TTA가 많은 지원을 많이 해주셔서 저희가 이렇게 번역을 하고 이런 것에 큰 도움을 받았습니다. 다시 한번 TTA에게 감사드립니다. Thank you, TTA. 네, 오늘 여기까지 하겠습니다. 감사합니다.